Welcome to the AIA accredited presentation, The Value-Added Performance of Coated Glass. This presentation is the result of the collaboration of flat glass manufacturers, also referred to as float glass manufacturers. NGA is a registered provider with the American Institute of Architects Continuing Education Systems. This course on coated glass fundamentals is registered and accredited by the American Institute of Architects, and one learning unit is awarded to architects for completing this presentation. This presentation will study the manufacturing process for coatings applied to glass, the improved performance values that come from the use of particular coatings, followed by a case study demonstrating the cost savings that can be achieved as a result of using coated glass products. The learning objectives for this session include: list reasons glass is coated, compare and contrast reflective and low E coatings, describe the difference between U value and solar heat gain coefficient, and outline the 3 cost-saving opportunities provided by coated glass. Now let's get started. To begin, let's address why glass is coated, if at all. Coatings are designed to impact specific properties to the visible portion of the spectrum, which is 380 to 780 nanometers. Coatings can significantly improve solar and thermal performance of the glass without modifying the glass itself, by modifying the reflectance and transmittance properties of the glass. There are also coatings that are designed to change the surface characteristics of the glass. Examples are hydrophilic and hydrophobic coatings, and microscopically rough surfaces for light scattering. Coatings may also serve as filters. Coatings can change the transmission, reflection, and absorption characteristics at different wavelengths of the solar spectrum, altering what the human eye perceives. Remember, percent transmission plus percent reflection plus percent absorption will always equal 100%. The visible appearance of the glass may be altered by varying light transmission, or varying light reflection, or changing the color of transmitted or reflected visible light in the visible spectrum. Coatings can also change solar and thermal performance of the glass by reducing the amount of the UV spectrum transmitted through the glass, reducing the near-infrared portion of the spectrum transmitted, which is felt to humans as heat, or reflecting far-infrared energy. Essentially, coatings can be designed to modify the look and thermal performance of the glass. Other uses for coatings include changing the surface properties of the glass in order to improve surface abrasion effects, for instance, a diamond-like coating, to reduce the reflectivity for commercial, solar, or lighting applications, to improve resistance to chemical attack, or create barrier layers to change the surface chemistry effects, or to change the surface effects of glass that is exposed to moisture, making it hydrophobic or hydrophilic, for instance, low-maintenance glass. There are multiple ways coatings can be applied to glass. For instance, monolithic or one piece of glass has 2 surfaces available, those being the air side or upper side of the glass that is made at a float glass plant, and the tin side, which is the bottom side of the glass exposed to the tin bath. In addition, laminated glass consists of 2 pieces of glass bonded together with an organic inner layer, and has 4 surfaces that are available for coatings: the outer surfaces and the inner surfaces bonded to the organic interlayer. Perhaps the most important use of coatings is for insulating glass units, typically called IGUs. If the IGU is double glazed, it has 2 glass lights with 4 surfaces available for coating. If the IGU includes a laminated glass light, or is triple glazed with 3 lights, there are 6 surfaces available for coatings, all of which may impart different properties to the final IGU product. This graphic shows the surface numbers applied to a monolithic piece of glass. They are numbered surface 1 and surface 2, starting from the outside or weather side to the inside or interior of the building. Each piece of glass has 2 surfaces which get a number no matter the construction. Here is a typical laminated glass construction where the surfaces are numbered from 1 to 4 from the exterior to the interior of the building. The interlayer itself is not numbered. This diagram depicts a typical dual-pane insulating glass unit, where the surfaces are numbered from 1 to 4, again from the exterior to the interior of the building. In this example, a low-E coating is located on surface 2, depicted by the thin black line. The cavity in the center is sealed and is not exposed to the outside air. This diagram depicts a dual-pane laminated insulating glass unit, featuring monolithic glass on the exterior of the building with a low-E coating on surface 2. The interior pane of the IGU is made up of a laminated glass light, with surface 6 being the innermost pane. As in the previous diagram, the cavity in the center is sealed and not exposed to outside air. There are 2 widely employed methods for coating glass. Pyrolytic or hard coat glass is produced by a method called atmospheric pressure chemical vapor deposition, which condenses a chemical vapor onto the hot glass surface within the float process. Sputtered glass coatings, sometimes referred to as soft coat, are produced by the magnetron sputter vacuum deposition process in large area high vacuum coaters that are a separate process from the float glass production. Metals and semiconductors are alternatively layered upon the glass surface. Properties of the final glass product are highly controllable, including light reflection, solar control, infrared reflection, color, surface durability, and other properties. The pyrolytic process, also called hard coat or online, can be broken down into either a vapor or liquid deposition process, which simply refers to the coating delivery system. Either delivery system for the pyrolytic process can be used to produce low-E coatings. However, the industry seems to favor the vapor deposition process due to cost and performance advantages. In either case, pyrolytic products are created by spraying the coating onto the glass in a process called online deposition. The coating is sprayed onto the glass while in the hot end of the float glass manufacturing process, when the glass is still semi-flexible and has not cooled to a rigid room temperature state. In general, high temperature application is the reason pyrolytic coatings are very durable because the coating is fused both to itself and to the glass surface. The pyrolytic coatings are metallic oxides, usually consisting of a fluorine-doped tin composition that has electrical conductivity properties. As the coatings are fused to the glass surface, they are very durable. The hard coating provides a surface that makes this type of glass easy to transport and store and is readily heat strengthened or tempered. They also resist corrosion, and this type of coating can be specified for monolithic and surface 1 use. When processing IGUs with pyrolytic coated glass, there is no need for edge deletion of the coating. This simply means removing a portion of the coating at the perimeter of the glass to ensure no coating is exposed to the atmosphere. To summarize, pyrolytic coatings are known for their durability in a wide range of environments, their shelf life, the ease of tempering with largely unchanged appearance, their scratch resistance during processing, that they're bendable and largely unaffected during the fabrication processes. They have moderate performance as low-E coatings, which can be used internally or externally in an IGU or on monolithic glass. Finally, they are often used in conjunction with tinted glass to improve solar performance. Pyrolytic coatings are most often used when storage and handling or environmental conditions are in question. They are also used when solar heat gain is considered more important than U factor. Sputtering is the other major coating technology, sometimes referred to as soft coat. Sputtering is a process whereby an ionized gas molecule is accelerated towards a metallic or semiconductor target material under high vacuum. The momentum of the gas molecule dislodges a target atom, which is transferred to the glass surface. The material being sputtered builds up atomic layer by atomic layer, and a magnetic field is created to drive the ionized gas toward the target, which is the name of the process itself, magnetron sputtering. This picture depicts what is going on inside the high vacuum chamber of magnetron sputtering equipment. In general, you can see the gas flows in through gas bars along the length of the target. The magnets mounted behind the target create a plasma zone, which energizes the gas molecules in order to impart momentum high enough to knock the target atoms loose. At the bottom of the diagram, you can see the glass passing under the target where the target atoms or molecules are building up. There are benefits associated with using the sputtered coating approach. The key difference being the ability to engineer coatings layer by layer, each layer having a specific purpose. This opens up a range of options to the coating engineer in order to enhance or suppress a given characteristic. The high-performance sputter coatings can provide optimized solar control or low-E properties, which maximize saving opportunities. They are spectrally selective in order to allow for daylighting applications. There are a range of products that can be cut, edge-seamed, and tempered from stock sheets. With sputtered coated products, there is better control of the aesthetic of a glass and architectural applications. And finally, certain sputtered coatings are being designed to resist the abrasive effects that early coatings exhibited. This makes them more user-friendly in terms of fabricating or even for monolithic and exterior IGU surfaces. Uses of sputtered coatings include high-performance coatings for commercial and residential buildings specifically designed for thermal and aesthetic characteristics. And their adjustable aesthetic properties provide sharp optics with specific color rendering. More uses of sputtered coatings are for moisture and soap scum resistance for use as shower enclosures, heat-treatable coatings that allow for stock sheet cut-down, edge treatment, tempering, and lamination, and their ability to be bent. Coatings may be used to produce highly reflective surfaces or mirrors. Mirrors are the second most important coating after the low-E coating. In North America, most mirrors are silvered mirrors, while in Europe, aluminum was used until the mid-80s. More than 900 million square feet of mirror is produced each year. Backside or second surface mirrors are produced using a wet coating process that employs mirror paint. The paint is applied as a wet film on the glass and then is dried in a furnace operation. Applications include interior and commercial mirror products, automotive and solar products like bent mirror reflectors. Mirrors can also be first surface, which means the surface with the reflective coating applied faces the eye. First surface mirrors are produced by sputtering highly reflective coatings such as chrome or aluminum onto the glass surface. Applications of first surface mirror include the electronic equipment, solar, and automotive markets. A chemical reduction method known as electroless plating is used to apply copper and silver. The chemicals are applied through a spray bar onto the glass surface. First surface mirrors can be produced in a large area vacuum sputtering coater. Metal targets such as aluminum or chromium are used within the coater to sputter ultra-thin metal layers onto the glass surface. As a first surface product, a double reflective image is avoided when compared to the second surface mirror, which means most of the visible light is directly reflected, which equates to a higher percentage of reflected light. Another method of producing first surface mirror is by using the pyrolytic method within a float furnace. This particular coating is sometimes referred to as a hard coat glass. A pyrolytic reflective product is partially reflective, allowing visible light transmission, such as two-way or transparent mirror applications, when the coated surface is installed facing the subject matter. The purpose of transparent mirrors is to create an environment that allows for unobtrusive observation. These are used in interior settings and are primarily used when discreteness is necessary. More examples of two-way mirror include uses such as focus group observation, police lineups, security, and surveillance applications. One might ask, how can glass be modified with coatings? As we've discussed, coatings are designed to impart various properties to glass, such as for solar control, reflected color, visible effects, and low E or infrared reflection aspects. Today, architects can choose from a wide range of coated glass products that meet different criteria for functionality and performance, including visual and thermal aspects of glass. Glass properties are altered with the addition of a coating. Generally, this can be thought of in terms of adding value to the glass product in some way. Coatings are designed and manufactured to impart a change to the performance of standard float glass types, and are generally manufactured by two processes: the pyrolytic process on a float line, or the sputtered process offline in a large area vacuum coater. Two important products are reflective and low E glass. There is a reason that window and door manufacturers offer coated glass in their products. Studies show that fenestration products represent the greatest heat losses in a building. This pie chart shows typical residential heat loss, with fenestration accounting for 41% of the dwelling's heat loss. Considering that energy is becoming more expensive, conserving it is one way for the building owner to save money. The product most used to conserve energy loss through glass is a low E product. Low E glass is designed for a thermal performance improvement. Low E glass used in fenestration products improves its U value. This improvement works in two ways. It can limit the amount of solar heat gain into a building in the summer in southern climates, or it can reflect heat back into a building in the winter in northern climates. Low E glass is designed to allow daylight to be transmitted into the building at a specified amount or percent transmission known as visible light transmission. Low E glass also blocks certain percentage of UV transmission, which can be damaging to furnishings and interior surfaces. UV contributes to 50% of fading along with visible light and heat. A certain amount of solar energy is transmitted through the fenestration product in the interior of the building. The coating design engineer has the ability to impart changes to the glass properties, such as visible light transmission, or VLT, which affects daylighting amount and glare, or UV transmission, which can cause damage to surfaces, flooring, and fabrics. The coating design engineer also has the ability to impart changes to infrared transmission, or heat. As noted here, total solar energy transmission is the sum of UV, visible light transmission, and near-infrared wavelengths passing through the coated glass. Emittance refers to the amount of heat a surface can radiate. A so-called perfect black body can emit heat at a value of 1. A perfect non-radiant product would thus have a rating of 0. Low E glass is designed to have as low a value as possible. High-performance low E glass products have been designed to have an emissivity of less than 0.04. U factor, sometimes referred to as U value, is a calculation of the amount of heat conducted through a material or series of materials. The lower the number, the better the material or assembly is at blocking heat transfer. For instance, standard float glass has a U factor close to 1 British thermal unit, or BTU, per hour, whereas a high-performance low-E product used in a well-designed dual-pane IGU can improve U factor significantly, up to 4 times better. R value is the inverse of U value. It is usually used to measure and denote a low thermal conductive building material, such as fiberglass insulation. The higher the number, the better the material is at reducing heat transfer. Solar heat gain coefficient is the ratio of solar heat gain entering the space through the fenestration product to the incident solar radiation. Most simply put, it is a ratio that includes directly transmitted solar heat and re-radiated absorbed solar radiation. Finally, shading coefficient is a measure of the heat gain through glass from solar radiation. Specifically, the shading coefficient is the ratio between the solar heat gain for a particular type of glass and that of 1/8 inch thick clear glass. In effect, the lower the number, the better the performance. 1/8 inch clear glass would have a shading coefficient of approximately 1. Light to solar gain ratio identifies a product's visible light transmitted divided by its solar heat gain coefficient. Relative heat gain, or RHG, is a measure of solar gain combined with a product's U value or conductive heat gain. The evolution of window glass has improved comfort, energy efficiency, and the lifespan of typical home furnishings. Heat loss is reduced with lower U factor. The table shows step improvement in performance as you move from monolithic to IGU to coated glass in IGU. With insulation, glass temperatures are closer to room temperature, which improved occupant comfort. As an example, we have progressed from monolithic to dual pane and cover data highlighting light to solar gain ratio with respect to visible light and solar heat gain. U factor insulation improves respectively from monolithic uncoated to low-E IGU with gas fill. Solar energy is the energy transmitted in the range of 300 to 2500 nanometers. Solar transmittance is defined as the percentage of ultraviolet, visible, and near-infrared energy within the solar spectrum that is transmitted through the glass. This describes how much UV, visible, and near-infrared energy is allowed inside a building through its glass. Solar energy can be transmitted, reflected, or absorbed by the glass. This slide shows the electromagnetic spectrum. Most of us think of visible light as a color rainbow. However, we are all aware of UV light or shortwave infrared light given our exposures to tanning beds or even our home oven. The visible spectrum is just a thin slice of the overall spectrum. Of the electromagnetic spectrum, the solar spectrum, consisting of ultraviolet, visible, and near-infrared energy, is from about 300 to 2500 nanometers. The visible light spectrum, as seen by humans, is from 380 to 780 nanometers. This graph shows the visible spectrum, the rainbow arrow, and the transmission effects of a sputtered coating with a single, double, and triple silver layer. The sputtered coating with silver layers allow most of the visible light to be transmitted. However, transmission of UV and infrared light is greatly reduced. If it is not transmitted, it means it is absorbed or reflected back to the source environment. Silver is the workhorse. It addresses solar reflection. Adding more silver means a lower emissivity and lower solar heat gain. Adding a fourth silver layer would lead to diminishing returns. This graph represents the reflective properties of sputtered Loewy coatings, made up of single, double, and triple silver layers. Energy Star is a joint program of the Environmental Protection Agency and the Department of Energy. Its goal is to help consumers, businesses, and the industry save money and protect the environment through the adoption of energy-efficient products and practices. The Energy Star program is utilized by the residential market as a value proposition or product differentiator. Different fenestration products are designed for a given region and performance requirements, or may be designed to be universally used in any region. This is the Energy Star MAP version 7 for the United States as of August 2023. Loewy coatings provide a means to obtain the energy requirements of a given region. The northern region is driven by U-value performance and, if possible, higher solar heat gain in the farthest north. Products are driven by best thermal performance or U-value of 0.22 or lower and with solar heat gain greater than or equal to 0.17. Loewy coatings may be specified for the third surface to increase solar heat gain. Additionally, in the coldest regions, a surface 4 coating may be specified to further improve thermal performance. The north-central region includes both heating and cooling loads, so is neither dominated by U-factor or solar heat gain requirements. In general, a U-value of 0.25 or less and a solar heat gain of 0.40 or less are required. The south-central region includes heating, but consists mostly of cooling loads, so is neither dominated by U-factor or solar heat gain requirements. In general, a U-factor of 0.28 or less with solar heat gain coefficient value of 0.23 or less is required. The southern region is dominated by cooling energy use. U-factor is not dominant with a requirement of 0.32 or lower. Rather, a low solar heat gain coefficient is required at 0.23 or less. Low solar heat gain coefficients may mean sacrificing visible light transmission. However, lower levels of light transmission to reduce glare in a building may be desirable. In summary, Loewy coatings are now required across all climate zones to either help meet low solar heat gain coefficient requirements in the south or the low U-factor requirements in the north. Loewy coatings are necessary to economically produce glazing products which meet code requirements that become ever more stringent. The commercial market continues to utilize an ever-expanding line of Loewy products which provide an ever-increasing level of performance necessary to meet the demanding ASHRAE and IECC codes. This section will address a building energy saving simulation that compares high-performance fenestration product use. The building described on screen was simulated in both Chicago and Miami, with the properties as shown. The 2004 version of ASHRAE 90.1 was used since this was an existing building. Insulating clear float glass is to be compared with high-performance coated glass on clear float glass. This chart shows a performance comparison for various glazing options. Different applications and different regions of the country use different combinations of glass in the IGU to maximize the benefits desired. For instance, the chart shows that combining a Surface 2 and Surface 4 low E coating in an IGU provides the best U factor with a fairly high visible light transmission. The numbers referenced on the vertical axis will be used again in subsequent slides. This chart shows the annual heating impacts of high-performance glazing compared to clear insulating glass units. Configuration 1 is a clear IGU with air fill. All other data is compared to Configuration 1. Positive bars mean reduced energy consumption for heating. Negative bars imply an increase in energy use. For instance, looking at Configuration 3 in Chicago, there will be a reduced energy consumption of 80 gigajoules compared to a clear IGU. When reviewing the Miami results, they are fairly similar due to the low heating needs in that region. Alternatively, there are generally higher energy savings in Miami when analyzing cooling impacts compared to Chicago. It can be seen that there is a bigger gain possible in a cooling-dominated climate, as the cost for cooling is typically greater when compared to the cost of heating. This slide is the total energy savings combining both heat and cooling energy consumption as one value. Notice the addition of low-E coated products provides a significant energy reduction compared to a clear IGU. Energy consumption reduction in Miami is generally more than in Chicago because it takes more energy to cool than to heat. In summary, cost savings are realized from the reduction in energy consumption. There are significant energy savings with the use of low-E coated glass. There is an ability to reduce HVAC system sizing due to reduced energy need. Overall energy consumption is reduced in both heating and cooling when using low-E coated glass, and savings will continue for the life of the building. There are other coatings that can provide benefits over uncoated glass. Specialized coatings can impart characteristics that include surface durability or hydrophilic properties. Specialized coatings have been optimized for shower enclosures to reduce the amount of soap scum and other shower products from sticking to the glass surface, making it easier to clean. There are coatings which are designed for exterior applications that impart low maintenance aspects to the surface. There is a photochemical effect and a surface tension effect. Low-maintenance glass products employ photocatalytic properties, which, in combination with moisture and UV radiation from the sun, decompose organic materials that are on the surface. UV radiation is reflected from many surfaces and is also present on cloudy days, so the process is working most of the time. The surface properties of low-maintenance products can impart a sheeting or droplet action when moisture is present. The hydrophilic property of these coatings causes the decomposed residue to be washed off the glass surface, for instance during a rain. This sheeting action also helps the glass dry faster and with fewer droplets spotting or streaking. This picture depicts the difference between normal droplet formation on the glass and the hydrophilic action of low-maintenance glass. The benefits of low-maintenance glass include the breakdown and loosening of organic dirt over time on the coating surface, a sheeting action that allows for better rinsing, faster surface drying with minimized spotting, UV transmittance that is reduced by about 20%, and solar heat gain coefficient that is decreased by about 4%. And finally, photocatalytic materials have been proven to have a positive impact on indoor air quality. During the photocatalytic process, hydroxyl radicals are created on the coated surface. These hydroxide radicals participate in oxidation reduction chemical reactions that break down nitrogen oxides and convert them into harmless nitrates. Finally, here is a depiction of the sheeting action of low-maintenance glass on the right compared with conventional uncoated glass on the left. Here are a variety of additional resources available to learn more about coated glass. And please consider visiting the websites of these industry organizations for additional information. There are several software resources available, and we also recommend checking with your glass supplier as there may be many programs available to customers and partners that incorporate the properties of their specific coated glass products into design programs. As a reminder, here are the objectives we intended to address today. List 2 reasons glass is coated. Compare and contrast reflective and low-E coatings. Understand the difference between visible light transmittance and ultraviolet. Describe the 3 cost-saving opportunities provided by coated glass. Thank you for your participation in the Value-Added Performance of Coated Glass AIA accredited presentation.